Greetings and welcome to another installment of Quantslob. This is 16, if you can believe it, in our basic application series. This time around, we're going to take a quick peek at the basics of counting. And when I say counting here, I'm not necessarily talking about 1, 2, 3, 4, although it certainly is quite related. We're actually talking about combinatorics. Combinatorics is all about combinations, the selection of values or objects from within a larger collection. Combinatorics has many, many important applications. Recall back in our probability sampling distributions mini-series, there we looked at a number of different sampling distributions for proportions. Then we did not really spend any time talking about how these sampling distributions were calculated, but it turns out that calculating these sampling distributions relies on combinatorics, and it is with this application in mind that we're going to focus our brief exploration here. So, to illustrate, suppose we have 6 pizza toppings here, and we want to know how many different pizzas we can make with 3 unique toppings from our selection of 6. Certainly, one way to get to our answer is to simply enumerate or count all of the possibilities here. And with a little bit of patience, doing so, we find that there are 20 possible 3-topping pizzas that can be made from 6 available toppings. In the language of combinatorics, we call this scenario 6 choose 3. This is simple shorthand for how many combinations of 3 unique items can be chosen from within 6 unique items. And to illustrate a way to think about solving these sorts of problems more generally, we turn to our good friend Pascal's triangle. And of course, Pascal's triangle is named after the great mathematician and frame welder Cooter Pascal. I suspect that someone is having a little bit of fun at our expense. Our Quantslob fact checker is out for the week on vacation, but I am quite certain that Pascal's triangle is named after the great 17th century French mathematician Blaise Pascal and not Cooter Pascal, so I apologize for that. So moving on here, back to Pascal's triangle. Let's break this down. What are we looking at here? First thing we notice is that, well, it bears resemblance to a triangle. It's a triangle filled with numbers, or more specifically filled with counting numbers or natural numbers. At the top, we have the number 1 at the pinnacle. Along the right and left sides here, we also see 1s. Once we have the 1s on all the sides here, the 2 sides, all the rest of the numbers can be filled in with simple addition. Notice the 2 here near the top. This value is simply the result of adding the 2 numbers above it, the 2 1s. And this simple pattern holds for all of the non-edge numbers we have. 3 is the result of adding 2 to 1, and 3 plus 3 is 6, and so on. Okay, so what does this have to do with pizza toppings here? Well, to show you, what we're going to do here is we're going to number the rows, but we're going to do this in a very particular way. The very top row, the pinnacle here, we're going to call row 0. Then we're going to count up all the way down the triangle. In this particular example, the graphic here that we have goes down to row number 7. In theory, of course, it keeps going, but this will serve us perfectly fine for this application. Not coincidentally, we're going to focus here on row 6. We'll zoom in on it. We're going to call the leftmost entry here on this row choose none. The next entry, choose 1, and all the way to the rightmost entry, we're going to call choose 6. And so, do you see it? 6 choose 3 right here is 20. This is the result we just derived by counting all of the possibilities. Pascal's triangle provides the answer to how many 3-topping pizzas can be made from 6 available toppings, and how many 2-topping pizzas can be made from 5 available toppings, and so on and so on. And of course, it doesn't just work for pizzas, but a vast variety of problems involving combinations. And there's a more direct way to solve these sorts of problems, and we're going to pick this up in counting 2. And that's it. That's going to do it this time around. Thank you very much for tuning in. I really do appreciate it. And don't forget to stay tuned for more Quantslob. Greetings and welcome to another installment of Quantslob. This is 17 in our basic application series. This time around, we're going to take a peek at part 2 of the basics of counting, or combinatorics. Recap. Counting combinatorics is all about selecting values or objects. So, For example, how many different 3-topping pizzas can be made from 6 available toppings? In the language of combinatorics, 6 choose 3. Well, one of the ways we can get to our answer is to simply enumerate or count all of the possibilities. And doing so, we find that there are 20 possible 3-topping pizzas that can be made from 6 available toppings. 6 choose 3 is 20. We can find the answer to how many 3-topping pizzas can be made from 6 available toppings in Pascal's triangle. In fact, we can find the answer to any n choose k problem. No problem. Here in this example, we visit row 6 here, starting at choose 0, which corresponds to the far left 1 here. We count over to the 4th entry, choose 3, and we arrive at our answer, 20. Notice that here in Pascal's triangle, the row sums, that is the sum of the numbers in each row here, is equal to the number 2 raised to the power of the row index. For example, the row sum of row 6 is equal to 2 raised to the 6th power, which is 64. So returning to pizzas, thinking about pizzas, what this means is that if we have 6 available toppings, there are a total of 64 different pizzas we can make. For example, there is only one way we can make a pizza with no toppings, and there are 6 ways we can make a 1-topping pizza, one for each available topping, and so on. There's a more direct way to compute n choose k. And here's the equation, and there's a lot going on here, so let's break it down. Let's take a look. On the left-hand side of the equality here, we have a capital C here that is subscripted with k and back subscripted with n here. This is the common mathematical symbol that means, or reads, n choose k. The exclamation mark here that we see appearing 3 times on the right-hand side of the equality denotes the factorial operator. And of course, factorial is named after the great mathematician and frame welder Cooter Factorial. Am I not logging out of my computer at night? Keep doing that. I sincerely apologize. The factorial is not named after anyone. I'm quite certain of that. A little piece of advice for all of you. Screen your interns. The factorial is sort of a cumulative product performed on the collection of all counting numbers up to and including the integer value that precedes the exclamation mark. So that's a big mouthful, but it's really easily conveyed by example here. So 5 factorial, for example, equals 5 times 4 times 3 times 2 times 1, which equals 120. Notice here, for the sake of simplicity, that 6 factorial is equal to 6 times 5 factorial. So all's well and good. But one wrinkle we need to know about is the somewhat counterintuitive fact that 0 factorial is defined as 1. Now, I say counterintuitive, but if we look at this through a mathematical lens, it makes perfect sense. The unit, the number 1, is the identity in multiplication, and 0 factorial really represents an empty product. So it makes sense. Anyway, let's go ahead and take our combination equation for a spin here. So back to our 3-topping pizza. 6 choose 3. We can solve this no problem here with our formula. So let's go ahead and expand this out. We notice that here we have a lot of cancellation after we've expanded out the numerator and the denominator. And needless to say, computers nowadays can solve these sorts of combinatoric problems effortlessly. And that's it. That's going to do it this time around. Thank you very much for tuning in, and don't forget to stay tuned for more Quantslob. Greetings and welcome to another installment of Quantslob. This is 18 in our basic application series. This time around, we're going to take a look at the sample. Although I will tell you that this title may be something of a misnomer here. Especially with the growing popularity of applied statistics, researchers nowadays spend more and more of their time head down in one data set or another. And of course, the term itself, or title, data scientist, seems to reflect an emphasis on data. For this video, we're going to start by relating this thing data to something with which we are already quite familiar, simply and broadly, impressions. All statistical samples are impressions. All samples or data sets, all those that have been, are today, or ever will be, are, in the abstract, ultimately impressions from some greater reality here. Now, if you've seen our Quantslob foundational series, this picture should look fairly familiar. A sample or data set is a realization from some population. This picture, however, as it stands, for our purposes, is incomplete. We need a third dimension to complete our triad. A mechanism, some process by which an impression has been manifest by reality. Now, the appeal of this broad relationship is that it is completely relatable. Even someone who has never seen a data set up close, or someone without any understanding of stats, can easily relate to this simply because everyone has impressions of the world around them. We are, all of us, host to personal impressions of countless themes. And as you can see, this is true even for Slobby, our favorite 3D emoticon here on Quantslob. Okay, so question. Why is it that people may possess varied impressions of the same theme? So for example, consider the theme roller coaster. One person here may have gained the impression that roller coasters are fun and exhilarating, while yet another person may hold the impression that roller coasters are terrifying. For another example, consider chess boxing. Now, one person might say that chess boxing is an ingenious sport that tests combatants' intellectual and physical prowess, while another person may say, well, this is just the most ridiculous and baffling thing on the face of the earth. Okay, so you get the idea. Nothing earth-shattering here. Personal impressions vary. So how does this fit into our paradigm here? Well, I think in this context, it's quite clear that variability in personal impressions is owed, albeit in a potentially extremely complicated way, to what we're calling our mechanism here. Some mechanism or process that has somehow conveyed or coded snippets of reality into personal formative content. To really crystallize our thinking here, be reminded that there's a very familiar language or vocabulary around this. We speak commonly of externalities, things like fate, destiny, luck of the draw, and internalities as well, personal biases, inner self. Okay, so that's as far down this rabbit hole as we're going to go for this video, but we are right where we want to be. The mechanism, the third member of our triad, can be thought of here as a revelatory process by which reality manifests information. And if we are interested in how the impression of scientific information, like a data set, is differentiated from something like personal impressions, this is where we need to look. We're right where we need to be. So what is it that makes the mechanism that leaves the impression of scientific data different than that of personal impressions? Well, one thing I think that would come to mind for most people is simply measurement, or the science of metrology. A data set contains explicitly recorded attribute values, numbers, labels that are hopefully documented in a structured, consistent way and across well-defined units of observation. Another differentiator is that we, or someone, has attempted to take control and force reality to reveal itself or leave an impression in a particular way. And this, of course, as you could imagine, includes sampling methods like randomization. To repeat the point here, randomization or any other deliberate means of tapping reality is a property of the mechanism, which is why it is unadvisable to qualify an actual sample, an impression, as being random. Randomness is not a property of an impression or a data set. It is a property of the process that manifested it, the mechanism. In modern applied data science, data is what people work on all day. Sometimes parameter estimates and their standard errors are calculated, thereby tacitly suggesting some population. Sometimes the mechanism is explored, the means of sampling or measurement, but often only as a formality that has to be suffered through en route to the actual data set. And so in a data-driven world, we become, I think, too familiar with this hierarchy here. We mentioned in the Quantslob foundational series that the population, here some subset of greater reality, is the cornerstone of stats. And this assertion is difficult to challenge, as much of the advancement of stats and probability over the last 2 centuries or so has focused on gaining understanding of our inferential population. And I certainly don't want to belittle anyone's data set, as some have resulted from years of labor, passion, and various forms of sometimes extravagant expense. But in truth, impressions come and go, data sets come and go. It is the mechanism, the process by which reality manifests information that is the driving force, the building block of all knowledge. And this is true whether the knowledge be scientific in nature or personal or even anecdotal. The person you are today is a massive composite of impressions. But my question to you would be, how in the world did you get those impressions in the first place? It is the revelatory process here, what we have been calling simply our mechanism, that is the real superstar in all this, center stage. And so I know what you're all of you are wondering. What does Slobby, our favorite 3D emoticon, think of all this? There you go. 2 thumbs up. That settles the matter. And that's it. That's going to do it this time around. Thank you very much for tuning in, and don't forget to stay tuned for more Quantslob. Greetings and welcome to another installment of Quantslob. This is 19 in our basic application series. This time around, yet more on proportions. It's yet more because we have already learned quite a bit about proportions, not only earlier here in this basic application series, but going way back to our Quantslob foundational series. Such fond memories. Seems like just yesterday. Greetings and welcome all of you crazy Quantslob cool cats. This is negative 2,742 of our foundational series, and this time around we're going to kick off our introduction where we introduce our introducing of our intro to our introduction of our introducing of our intro where we introduce. Well, I think that was one of those ideas that looked better on the storyboard than as it actually came out, and besides, it wasn't really all that long ago. Anyway, back then we learned, among other things, from a data science perspective, we may think of proportions as a rising force in at least 3 different settings. We can talk about a proportion as a population parameter. We can also talk about a proportion as a sample statistic, and also as a random variable implicated by theoretical random sampling. This last setting is quite a bit more challenging to grasp than the other 2, but with familiarity comes understanding. From a notational standpoint, we commonly use lowercase upright p to denote a proportion in a population, that is a parameter. To denote a sample proportion, that is a sample statistic, we keep the same p here, but we put a little hat on it, so that's nice, got a little hat there. As a random variable, we keep the hat, and we use an uppercase leaning or italics p here on Quantslob. In our terminology and symbols microseries, we saw that we can put a little subscript here on our proportion symbol to remind us and make clear to anyone else exactly what it is we're talking about. Okay, so let's roll things back here a little bit. What is a proportion? Where does it come from? We can think of a proportion as a quantity describing in the aggregate the prevalence of some category or property among a collection of elements or observational units. So, for example, we can consider the proportion of occupied seats in a small conference room. So to each of our units, the chairs here, seats, we can ascribe an attribute, occupied status. And in this way, we can calculate our proportion of occupied chairs here. For another example, we may have a waddle of penguins here returning from a nice, refreshing swim and wonder what proportion are named Banu. Seems like a reasonable avenue of investigation. Assuming we have access to these penguins' first names, we can calculate our proportion. We have 16 penguins here, and look at that. 2 of them are named Banu. It seems like it would be a little bit confusing for them, but then again, who are we to stand in judgment of a bunch of penguins? Another thing we talked about is creating an indicator attribute. An attribute where we have converted a categorical label into a 1 or a 0. Admittedly, this extra step may add a little additional complexity, but it is very useful. By indicating over a categorical label, we are creating a quantitative attribute. And one consequence of this is that it turns out that the proportion of the category is the same as the average of the indicator, our indicator. Another important consequence, and one we have not introduced here on Quantslob, is that now that we have our indicator attribute, we can quantify how varied this attribute is. The so-called variance is a very useful way to talk about how varied a quantity is. And we have not yet discussed how to calculate variance, But it turns out that for a proportion, we can calculate the variance of our indicator attribute simply as a function of the proportion value itself. And this, by the way, is quite different and much more simple, fortunately, than with quantitative attributes more broadly. It turns out that the variance of our indicator is simply the proportion value times the value subtracted from 1. So, for example, if our proportion is, say, 5/7, then the variance of our indicator attribute is simply 5/7 times 2/7, which equals 10/49. For another example, if our population proportion is, say, 1/8 here, then our variance of this attribute indicator would simply be 1/8 times 7/8, which is 7/64. Proportions, moving on, whether they be population proportion, sample statistic, or even random variable, are very easy to plot and easy to convey by table. And lastly, here for this edition, we may speak of a proportion within an infinite population. And if you're not familiar with this, this may seem bizarre, since this might suggest that calculating our proportion would require dividing by infinity. But this is not an issue, it turns out. For one thing, we can simply define a proportion value within an infinite population, and we've already done this plenty of times here already on Quantslob. Or we can conjecture or hypothesize a proportion value within an infinite population. No problem. Moreover, using commonly established properties of numbers, we're allowed to assert things like the proportion of even integers within the collection of all integers is 1/2, or that the proportion of real numbers in the unit interval that are less than 1/5 is 1/5. Not at all an issue. And that's it. That's going to do it this time around. Thank you very much for tuning in, and don't forget to stay tuned for more Quantslob. Greetings and welcome to another installment of Quantslob. This is 20 in our basic application series. Like most content creators, we try to make each installment as freestanding or self-contained as possible. But for this mini-series, we're going to build the top concepts we've already seen earlier in our foundational series and earlier back even in this basic application series. And you can see we got this crane building something like, I don't know, a great edifice of wisdom, if you will, as a metaphor. We were originally going to contract out with Disney to create this animation, but we thought that using a second-rate operation like Disney for content might jeopardize the Quantslob brand, so we just went with this, and pretty happy with the way it came out. This time around, we're going to kick off our practical series on hypothesis testing of a single proportion. And I'm going to start by saying that there's an entire universe of rules, procedures, methodologies, and so on that govern the specification and interpretation and use of hypothesis tests. And for the sake of sanity, we're going to consider some here at the outset, as opposed to completely ignoring them and regretting it later. So first off, for any given investigation, we are allowed only a single research question. That is a single null and alternative hypothesis pair. Our hypotheses are fashioned before we look at the data, or even better yet, before the data is gathered. The mechanism that has produced or will produce our sample can be thought of as a proxy for theoretical random sampling. Now, we may hear these themes recited in different ways depending on with whom we are talking and their degree of zeal for a particular area of application. The first two rules can be bypassed so long as special adjustments or adaptations to our test procedure are made. And the third rule, of course, is inextricably tied to our definition and conceptualization of our reference or target population. In the context of performing a decision-based research hypothesis test, if we play fast and loose with these practices, we may find ourselves guilty of so-called data dredging. When highway or railway teams need to tunnel through a mountain or beneath a body of water like a channel, they often start at opposite sides and meet somewhere near the middle. So too, sort of, with a traditional decision theory style hypothesis test. On one side, we define our critical region here based on our alternative hypothesis, our pre-specified level of significance, and our assumption concerning the sampling distribution of whatever test statistic we're going to be using. On the other side, we take the result of our experiment and calculate our test statistic. And we sort of meet in the middle. Does our calculated test statistic land in the critical region? If so, we reject our null hypothesis in favor of our alternative hypothesis. Otherwise, if our calculated test stat lands outside our critical region, we do nothing. So what we're going to do here is we're going to set up a simple example of using the normal approximation to perform a statistical hypothesis test of a single population proportion. Then upcoming in this mini-series, we're going to drill into the details and offer a few more examples. So let's just try it out here. Suppose a friend hands us a coin and says that they believe it is loaded. So of course, we ask why they think it's loaded. And our friend simply says that a stranger gave it to them and said it was loaded. So we're going to resolve to test this claim statistically. So for the sake of example, the coin looks like a typical coin. There's nothing special or remarkable about it. We have no external or additional information about this coin. So we're going to assume that this coin is not loaded, meaning that it is a so-called fair coin. So our research question is this coin loaded? Often formulating our hypotheses requires some subject knowledge. A loaded coin is a coin that is not fair. That is, either heads or tails do not occur with the same frequency. This is reflected here in our alternative hypothesis. Our null hypothesis, on the other hand, is that the true population parameter proportion of heads is 1/2. That is, that the coin is fair. So we're going to flip this coin 50 times and record the outcome of each flip. And by the way, our reference population can be described as a superpopulation. Every possible flip and landing of this coin, or perhaps more accurately, every possible flip and landing of this coin over the next 50 flips over the next 10 or 15 or so minutes. So, okay, we're going to use a normal approximation here. What this means is that we're going to take our sample statistic, namely the proportion of flips coming up heads, and convert it to our so-called test statistic, a standard normal or Gaussian quantile. And the name we typically give this quantile is Z. Now, our first step here in a traditional decision theory style hypothesis test is to specify our so-called critical region. And for the sake of expediency, what we're going to do is I'm simply going to fashion our critical region as all the values of our test statistic that are less than -2.3, along with all the values that are greater than +2.3. Now we're going to flip this coin 50 times, and let's say for the sake of example that these flips result in a total of 30 heads. So our sample statistic p hat is 30/50ths, which simplifies to 3/5. This result of 30 heads and 50 flips with a null proportion of 1/2 results in this value for our test statistic. And we're going to detail the calculation soon upcoming in this mini-series, so don't even trip on that. This test statistic does not fall in our critical region. It is neither less than -2.3 or greater than +2.3. Since our test statistic does not land in the critical region, we do not reject the null hypothesis. That is, we failed to reject the null. In our little make-believe experiment with this coin, our 50 flips or trials, we did not encounter sufficient statistical evidence to overturn our assumption that the coin is fair. And that's really all there is to it. Now, we certainly omitted some details, but they are just details. The important thing is that we executed a full-on, full-blown statistical test. And we're going to detail how we calculated both these steps, that is, create a rejection region, and how we transformed p hat into our z-score immediately upcoming in this mini-series. And later in this mini-series, we're going to work through a couple more examples. And that's it. That's going to do it this time around. Thank you very much for tuning in, and don't forget to stay tuned for more Quantslob. Greetings and welcome to another installment of Quantslob. This is 21 in our basic application series. This time around, we're going to pick up right where we left off in part 1 of this mini-series with part 2. If you want to enjoy the blow-by-blow action, and I mean who would not, I suggest you watch this mini-series in full. You can find it playlisted under the Quantslob channel playlist tab. There you will as well find many other action-packed ready-made playlists. Okay, so let's do a quick recap here. Our friend finds themselves in possession of a mysterious, purportedly loaded coin. Observing that this coin seems quite typical and knowing nothing else about this coin, we fashion a statistical test. We assume we are in possession of a fair coin, but we are prepared to challenge this belief if the result of 50 flips provides us with statistical evidence to the contrary. In a traditional decision theory style statistical test, we have 2 distinct steps. The first is to fashion a so-called critical region of our test statistic. Then after our experiment, we take our results and calculate our observed test statistic. In our little make-believe experiment, our sample proportion of heads was 30 and 50. Using this value, our calculated test statistic Z was about 1.41. This value is not in our critical region, and so as a consequence, we failed to reject the null hypothesis. So let's dig into some of the details here. Our world orbits our null sampling distribution. This is true not just for this example, but throughout statistical hypothesis testing. So this is our theoretical sampling distribution of proportion of heads when the number of flips or trials is 50, and the proportion of heads in our population is 1/2. This distribution, by the way, is very closely related to the so-called binomial distribution. This distribution here, the proportion of heads from a theoretical random sample of 50 flips, can be approximated or modeled, if we prefer, by a standard normal random variable. The probability that our standard normal random variable is between -2.3 and +2.3 is about 0.98, or 98%. Converting a normal quantile region, like the region between -2.3 and +2.3, into a probability, like 0.98, can be done in a number of different ways. You know, the old school way is to use a table. The more modern approach certainly is to use software. We can use an online calculator. I've included links in the video description if you want to check out some resources. Okay, so I decided our critical region for a normal approximation test statistic Z be a region of values less than -2.3 or greater than +2.3. If the null is true, values inside this critical region occur with a probability of about 0.02. And by the way, just to be technically correct, this is true here whether or not the inequalities here are strict. Said simply, if the null hypothesis is true, values in the critical region are fairly rare. But here's where things get, I think, really interesting. It turns out that if our alternative hypothesis is true, values of Z that are far away from the center, like those in our critical region, for example, could be much more likely than we assume under a true null hypothesis. And just thinking logically about this, not thinking mathematically, values that are far away from the center not only constitute evidence against the null hypothesis, but potentially offer evidence in favor of the alternative hypothesis. And this is exactly what the proverbial doctor here ordered to help inform our decision concerning our hypotheses. This is the key insight behind really all decision-based statistical tests. We start a priori with a significance level, commonly notated with the Greek letter alpha, first letter in the Greek alphabet. The significance level can be thought of as a probability we will erroneously reject the null hypothesis, or said another way, the chance of committing a type 1 error. For this example, I decided on a significance level of 0.02, or simply 1 in 50. We can choose other values as well for our significance level. Our critical region is the region of values under our null sampling distribution that occur with probability equal to our significance level and represent the values that most strongly argue against the truthfulness of our null hypothesis, but additionally potentially argue in favor of our alternative hypothesis. Okay, so how did we transform our sample statistic into our test statistic? Or said another way, how did we convert our sample proportion into our z-score? Well, here we go. If you're seeing this for the first time, it may look a little bit daunting, but to sketch things out, we have a function we're calling f. This function takes 3 inputs here. The observed sample proportion, the total sample size or number of trials, in our example, the total number of flips, 50, and also the population proportion value under the null hypothesis, 1/2 in our example. Our function hands us back or returns our z-score test statistic. And we're going to take a closer look at this function upcoming next in this mini-series. And by the way, for the sake of thoroughness, this function can operate on our sample proportion as a random variable, in which case our function will return a standard normal random variable. Make sure to check out part 3 of this mini-series, and that is it. That's going to do it this time around. Thank you very much for tuning in, and don't forget to stay tuned for more Quantslob. Greetings and welcome to another installment of Quantslob. This is 22 in our basic application series. I have been reminded that I am under contractual obligation to mention that the following installment of Quantslob is being brought to you by our new parent organization, Slob Global Corporation. This time around, we're going to power on with part 3 of our practical series on hypothesis testing of a single proportion, picking up right where we left off in part 2. So we'll do a quick recap here. Our friend finds themselves in possession of a mysterious, purportedly loaded coin. To test this claim of loadedness, we fashion a decision theory style statistical test. We use a normal approximation, or if we prefer, the normal model. a standard normal distribution to approximate the sampling distribution of our sample statistic proportion of heads. In our first step, we set our test significance level to 0.02 or 1 in 50, which gives us our test stat critical region, or sometimes called our rejection region. In our second step, our observed sample proportion of heads was 30 over 50. Using this value, our calculated test stat Z was about 1.41. This value is not in our critical region, and so as a consequence, we fail to reject the null hypothesis. To transform our sample statistic into our test stat, we use this function here. So let's keep peeling back the layers. What is this? What are we looking at here? One piece of good news is that, like so much delicious nigiri, we can break this down into bite-sized pieces. Another piece of good news is that these pieces do reappear in many statistical applications, including other types of hypothesis tests. So understanding this particular application is certainly going to help us down the road. So let's start by zooming in on the numerator on the right-hand side, the top of the fraction. So what do we see here? What is this? Well, very simply, it's a difference between two quantities. We have our observed sample statistic proportion minus our hypothetical value of the population proportion, or the value of our population proportion under the null hypothesis. We can think of this difference as a measure of how far away our observation is from our assumed value in either direction. If our observation is larger than our assumed population proportion, this difference is going to be some positive number. Conversely, if our observation is smaller than our assumed population proportion, this difference is going to be some negative number. And of course, needless to say, if our observed sample proportion is the same as our hypothetical proportion, then this difference, the numerator on the right-hand side, is simply 0. The denominator here is where really much of the action is. This entire quantity is called our standard error. The value p times the quantity 1 minus p may look familiar. We visited this back in our proportions yet more installment. It is the variance of an indicator attribute. The variance in our imaginary infinite population of coin flips of the indicator attribute is heads. If the population proportion is 1/2 of the value under our null hypothesis, then this value is 1/4. And here is simply our sample size. In this example, the total number of flips or trials, 50. One really important thing that I want us to be aware of here, speaking loosely or conversationally, we can think of the standard error as an evaluation of the amount of volatility, uncertainty, or imprecision even of our sample statistic. Accepting the case where our observed difference in the numerator is 0, if our standard error is relatively large, then the magnitude of our test stat, our z-score, will be relatively small. Conversely, if our standard error is relatively small, the magnitude of our test stat will be relatively large. So let's grind this out. Let's just go ahead and plug our values into our function, and lo and behold, we sort of already knew this. Our trusty function returns to us a value of about 1.41. Before we close out this edition, I want us to consider another but mathematically equivalent way to express our function f. With a little bit of algebra, we can rewrite our function like so. And I showed the mathematics here to provide rigor, but if you're not comfortable with these operations, it's really not worth worrying about at this point. I don't think the big message or takeaway is that this function is equivalent to the one we were just looking at in terms of inputs and outputs. And I actually much prefer this representation, although it is not commonly utilized in introductory stats texts. And there's really two reasons I like this representation, and perhaps you will come to like it as well. The first is that the quantity here is a measure of precision. That is the precision of our sample statistic under theoretical random sampling given a true null hypothesis. And I think that for most people thinking about precision, or more loosely, certainty, is more natural than thinking about variance, or more loosely, volatility or uncertainty. The other reason I like this is, well, this representation involves one less division. It's just a little bit easier to look at and think about. Square root of the precision goes up, magnitude of our test stat goes up. Square root of the precision goes down, magnitude of the test stat goes down. Nice and simple, no problem. Make sure to check out part 4, and that's it. That is going to do it this time around. Thank you very much for tuning in, and don't forget to stay tuned for more Quantslob.
The preceding installment of Quantslob was brought to you by the good, honest, wholesome, hard-working people at Slob Global Corporation. At Slob Global, we put the SOB back in Slob.
Greetings and welcome to another installment of Quantslob. This time around, we're going to take a little break from our ongoing mini-series hypothesis testing of a single proportion to bring you the Marilyn Savant drama. This is our second purely topical video here on Quantslob, the other, of course, being our Simpsons Paradox video. A more scholarly title for this video might simply be the Monty Hall problem. But we chose our main title here out of deference to Ms. Savant, and also because drama is really a very appropriate word to describe this particular piece of history. I want to mention that there is a really excellent article written by Zachary Crockett for Priceonomics. The link is in the description, and it is highly recommended reading for anyone even slightly interested in this story. It was very close to 30 years ago that Miss Savant became embroiled in one of the most fascinating and even perplexing episodes in the history of modern statistics. Now, Miss Savant was something of a wonder kid, like a child genius, somewhat reminiscent of the chess grandmaster Jose Raul Capablanca and the great mathematician Srinivasa Ramanujan. All three, at a very young age, showed genius far beyond their years. In 1986, Ms. Savant began writing a column for Parade magazine titled Ask Marilyn, where readers would ask various types of scholarly questions and puzzles, and Ms. Savant would respond with a solution and perhaps some commentary. The Monty Hall problem is based on a game that appeared in the game show Let's Make a Deal, which was hosted for almost 3 decades by Monty Hall. In real life, if you can call a game show real life, this particular game appeared in a number of variations. The so-called Monty Hall problem, as it is known, is based on a specific flavor of this game, and it goes like this. A contestant would be presented with 3 doors. Behind one of the doors is some very desirable grand prize. Of course, the contestant would not know which door and would choose one of the 3. The host would then reveal one of the 2 remaining doors that does not have the grand prize, and the contestant would be asked whether or not they'd like to switch their choice of doors. And so the Monty Hall problem asks, assuming we want the grand prize, are we better off switching or keeping our original selection? By the way, on Let's Make a Deal, they would place sometimes a zonk prize behind one of the other 2 doors, like a goat, and I guess they did that to make the contestant feel especially humiliated if they lost. Anyway, so it was this question, sort of, some 30 years ago, that a reader of Parade magazine submitted to Ask Marilyn. It is important to note here that the solution to this problem had been known for many years prior to 1990, published and discussed without fanfare and without any sort of controversy that I'm aware of anyway. So Ms. Savant replied, and I'm paraphrasing, that yes, you should switch. By doing so, you improve your chance of winning from 1 in 3 to 2 in 3. This is and was generally regarded as the correct answer. Very neatly and concisely articulated for the reader, simple as that, and so of course everyone just gets on with their lives. Well, not quite. And by the way, if you've ever watched our Simpsons Paradox video, the answer is yes. I've definitely got Ms. Savant here volunteering to make a keg run. What in fact ensued instead was a hailstorm of rebukes and rebuttals. Mr. Crockett, in his aforementioned article, uses slightly more colorful language to describe the kind of storm that ensued. When I say hailstorm, we're talking literally thousands of letters. And so as if that is not bizarre enough, many of these rebukes originated from very high-standing academics and professionals, and some were, I think, unnecessarily vitriolic, and some of these letters to the magazine really smacked loudly of scientific dogmatism and chauvinism. And to be very candid, this matter of scientific dogmatism and chauvinism is not one upon which I'm really qualified to offer an authoritative exegesis. I am, however, prepared to explain solving the Monty Hall problem. And I want to offer two highly conceptually related ways to solve the Monty Hall problem, both of which evidently flummoxed Miss Voss Savant's detractors some 30 years ago. You should be able to access some code examples in the discussion to simulate the Monty Hall game. And we can also formalize the solution by crafting a so-called probability space. And we're going to save this for a future video. Enumeration. Enumeration is like the preschool of probability theory, or more accurately, really, it's sometimes viewed that way, much too juvenile for any self-respecting probabilist, but it works great for problems like this. It turns out, in fact, we can reduce this enumeration by employing a simplification rule, and that is we will always start by picking door 1. Each of the 3 rows in our table here reflects each possible location of the prize. Determining whether or not our original choice wins is very direct here. We can see that in the table. We need to determine the consequence of switching. Well, if our original choice is correct, then switching must lose because neither of the other 2 doors has the grand prize. In the second case here, the second row, the host must reveal door 3. Therefore, switching means that we will end up with door 2, the prize door. So we win. And the exact same logic holds for the third case here. Our simplified enumeration reveals that if we stick with our original choice, we win 1/3 of the time. However, switching wins 2/3 of the time. Okay, now, if we want to run with the big dogs, we'll need to come up with a symbolic solution. And of course, you know the Slob Nation deserves nothing but the best, so let's give it a go here. It turns out, with the help of Bayes' rule, this is barbarically simple. So much so that it might even be said that this solution may be seen as deceptively difficult. Okay, so you can see we've got these 2 nice random variables here, x and y we're calling them. For both, the domain contains 2 elements. What we seek here, of course, is the probability that we will win by switching. Of course, we already know the answer to this, but let's pretend we do not. What do we know? Well, we know that the probability of our original selection, the probability that it's correct, that is wins, is 1/3. And equivalently, the probability our original selection is incorrect, does not win, is 2/3. So how do we proceed here? Well, it turns out that we know or can easily determine the conditional probabilities. And we actually already did this during enumeration. If our original selection is correct, winning by switching is an impossibility. We will end up with one of the 2 doors here that do not have the prize. Therefore, the conditional probability win by switching, given a correct original selection, is 0. If, on the other hand, our original selection is incorrect, winning by switching must occur. No matter what, we will switch to the door with the prize. Therefore, the conditional probability win by switching given an incorrect original selection is 1. So our system, or space if you prefer, is fully defined. We know everything there is to know about it. The probability of the joint occurrence of win by switching and a correct original selection is equal to the probability of the conditional weighted by the probability of the condition occurring, and same for the probability of the joint occurrence of win by switching and an incorrect original selection. And we finally get to our sought marginal probability by summing over x and arrive at 2/3. When we defined this game a moment ago, we said something like, the host then reveals one of the 2 remaining doors that does not have the grand prize. In the rigor of mathematics, this statement is unconditional, meaning that the host always reveals one of the 2 remaining non-prize doors. However, if this is not true, for example, if the host only offered the opportunity to switch if the contestant's original choice was correct, then of course our proffered solution simply falls apart. We're going to soon pick back up with our exhilarating mini-series on hypothesis testing of a single proportion. You are not going to want to miss that. And that's it. That's going to do it this time around. Thank you very much for tuning in. I really do appreciate it. And don't forget to stay tuned for more Quantslob. Greetings and welcome to another installment of Quantslob. This is 23 in our basic application series, This time around, we're going to motor on with part 4 of our practical series on hypothesis testing of a single proportion, picking up right where we left off in part 3. If you want to enjoy all the action, and who wouldn't, I suggest you watch this mini-series in full. You can find it playlisted under the Quantslob channel playlist tab. So let's do a quick recap here. Our friend finds themselves in possession of a mysterious, purportedly loaded coin. Now, observing that this coin seems quite typical, and knowing nothing else about this coin, we fashion a decision theory style statistical test. We assume we are in possession of a fair coin, but we are prepared to challenge this belief if the result of 50 flips provides us with statistical evidence to the contrary. Now, we use the normal approximation, a standard normal distribution, to approximate, or if we prefer, to model the sampling distribution of our sample statistic proportion of heads. In this installment, we're going to look at a p-value version of a decision-style statistical hypothesis test, which is a little bit more popular, I think, nowadays. And there's actually really very little difference. The calculations are much the same, but there is a slight tweak in the methodology. In a p-value version of a decision-style statistical hypothesis test, we must still start by setting a level of significance. The probability of wrongly rejecting the null, otherwise thought of as the probability of making a so-called type 1 error. In our example earlier, we chose 0.02, 1 in 50. In a p-value decision test, we do not calculate a critical region as we do in a traditional decision theory style test. Rather, we immediately calculate our test statistic. And of essential importance here, the driving motivation behind making a decision between the null and alternative hypotheses is built around the basic idea that values that are far away from the center of the sampling distribution of our test statistic, our standard normal distribution, not only constitute evidence against the null hypothesis, but potentially offer evidence in favor of the alternative hypothesis. Our critical region or rejection region is a space that contains values that are rare if the null is true, and also contain values that may be common if in fact the alternative hypothesis is true. We set the probability of our critical region to be equal to our significance level in a way that is similar to the way in which we carved out our critical region earlier. To obtain our p-value, we're going to construct a region that contains values that are unlikely if the null is true, but potentially likely if the alternative is true. Sound familiar? A region with the smallest probability, that is the smallest area under our null sampling distribution here, but that includes our observed test statistic. In this case, from earlier, if you recall, about 1.41, the area probability of this region is our p-value. Another way to say this is, what would our quote-unquote significance level be if we required our quote-unquote rejection region to include our observation? And there are a number of resources that we can use to find this area here. We can use statistical software or a table or an online calculator, and I've included links to a number of resources in this video description for your enjoyment and exploration. Our result here, based on our observed test statistic, is 0.157 about. In other words, the combined area of the gold regions here is about 0.157. This is our p-value here. And our last step is to compare our p-value with the original significance level we specified. If our p-value is smaller than or equal to our significance level, we reject the null hypothesis. Otherwise, we fail to reject. And here, 0.157 is not smaller than 0.02, so we fail to reject, which of course is the exact same result we already obtained. Ultimately, when it comes to making a decision about our null hypothesis, either the decision theory style test we originally looked at or the p-value decision style approach will give us the same answer, certainly. Both of these flavors of statistical tests, that is the decision theory approach and the p-value decision style approach, are oriented towards informing a decision about the truthfulness of our alternative hypothesis, which in turn may promote a change in the status quo, a call to action here. This application occurs very often in industry. Like a common example is clinical trials, where a pharmaceutical company has to decide whether or not to scale up production and promotion of a new medicine. Another example occurs in quality control, where a manufacturer has to decide whether or not their production equipment needs to be inspected or serviced or maybe even perhaps replaced. There is a third flavor of statistical test, which is extremely popular these days, simply because many scientific investigations don't really implicate that some decision has to be made. And this is simply a measure or degree of evidence type statistical test. And I'd love to be able to use the term evidence-based to describe this third flavor of statistical test, but the term evidence-based has sort of been co-opted by a number of different disciplines to mean something entirely different. In any case, a measure of evidence statistical test is very much the same as what we just looked at. However, we do not specify a level of significance at all. The resulting p-value is simply interpreted as a degree or amount of evidence. The smaller the p-value, the more the evidence against the null and in favor of the alternative hypothesis. Make sure to check out part 5, and that's it. That's going to do it this time around. Thank you very much for tuning in. I really do appreciate it. Don't forget to stay tuned for more Quantslob. Greetings and welcome to another installment of Quantslob. This is 24 in our basic application series. This time around, we're going to power on with part 5 of our practical series on hypothesis testing of a single proportion, picking up right where we left off in part 4. Now, if you want to enjoy all the thrills and chills, I suggest you watch this mini-series in full. You can find it playlisted under the Quantslob channel playlist tab down there. So let's do a quick recap. Our friend finds himself in possession of a mysterious, purportedly loaded coin. Now, observing that this coin seems quite typical, and knowing nothing else about it, we fashion a statistical test. We assume we are in possession of a fair coin, but we are prepared to challenge this belief if the result of 50 flips provides us with statistical evidence to the contrary. Now, throughout this mini-series, we have used the normal approximation. So what does this mean? Well, it means that we use a standard normal or Gaussian distribution to approximate, or if we prefer, to model the sampling distribution of our sample statistic p hat, our proportion. Under the null hypothesis, this here is our theoretical probability sampling distribution of our random variable, proportion of heads, resulting from a theoretical random sample of 50 tosses. Now, if we transform these proportions into z-scores using our trusty function here, we end up with this. Both of these distributions are probability mass functions, meaning that the domain of values is discrete. The green path here shows the shape of a standard normal density function. And the idea is simple. Both describe similar probabilities for the same event. And to illustrate, let's place these two distributions side by side here. So, for example, the probability that z will be greater than 1. Our z-transform sampling distribution gives a little over 16% for this event. Our standard normal model gives a smidge under 16% for this event. That's pretty close. For another example, the probability that z will be greater than -2. Our z-transform sampling distribution gives a little over 98% for this event. Our standard normal model gives a little under 98% for this event. And again, pretty close. Or how about, if you recall, our original critical region, that z will be less than or equal to -2.3 or greater than or equal to +2.3. And again, fairly similar probabilities here. So one obvious question at this point is, under what conditions does the normal distribution provide a sufficiently accurate approximation to our sampling distribution? Well, let's consider some counterexamples here. Suppose we have a theoretical random sample of only 2 tosses of a fair coin, 2, not 50. Here, the normal approximation tells us that the probability that z is greater than 1 is about 16%, whereas in truth, under the actual theoretical sampling distribution, the probability is 1/4. That's a pretty big difference. For another, the normal approximation tells us that the probability that z is between -1 and +1 is about 68%, whereas in truth, under the actual theoretical distribution, this probability is 1/2. Another fairly big discrepancy. So we've come this far. Let's consider a couple more counterexamples. The deficiency of the normal model to approximate the sampling distribution of a proportion becomes even more apparent when the number of trials is small and the population proportion is away from 1/2, that is, towards 0 or 1. So suppose we have a theoretical random sample of only 2 coin tosses again, and that the population proportion of heads is 1/4, not a half, 1/4. Here, the normal approximation tells us that the probability that z is greater than 1 is, again, about 16%. We already know that. Whereas in truth, under the actual theoretical sampling distribution, the probability is 1 in 16. And that's a very big discrepancy. For another example, the normal approximation tells us that the probability that z is between -1 and +1 is about 68%. Again, we already know that. Whereas in truth, under the actual theoretical distribution, the probability is about 0.94. And that's another very big difference. So, when does a normal model in fact provide a sufficiently accurate approximation? Or said another way, when is it okay to use a normal model to approximate the sampling distribution of a sample proportion? Well, it really depends on the application. Now, some sources suggest that if the sample size times the population proportion is greater than 10 and the sample size times the quantity 1 minus the population proportion is greater than 10 here, then the normal distribution should be a satisfactory approximation to our theoretical sampling distribution of our sample proportion. This sampling distribution of a sample proportion, by the way, is very closely related to the so-named binomial distribution, and we're going to be taking a look at the binomial distribution upcoming here on Quantslob. And note, just for the record, that in our coin flipping experiment, we do in fact satisfy these conditions. An alternate rule is to take the product, the grand product of the quantity 1 minus our population proportion and the population proportion and the sample size here. And if this value is greater than 5, say 5, then again, the normal distribution should typically be a pretty satisfactory approximation. And once again, note that in our coin flipping experiment, we satisfy this condition as well. Make sure to check out part 6. And that's it. That's going to do it this time around. Thank you very much for tuning in. I really do appreciate it. Don't forget to stay tuned for more Quantslob. Greetings and welcome to another installment of Quantslob. This is 25 in our basic application series. Before we start here, I wanted to mention a couple of you have asked why we don't tape with a live audience. Well, it turns out we've tried this in the past, but it didn't seem like anyone in the audience, really applauded or laughed at any of the jokes. In fact, I recall I even noticed a number of our studio audience taking a nap during the taping. So we figured, why go to the extra trouble and the added expense? Anyway, this time around, we're going to keep rolling with part 6 of our practical series on hypothesis testing of a single proportion, picking up right where we left off in part 5. If you want to enjoy all the thrills and chills, I suggest you watch this mini-series in full. You can find it playlisted under the Quantslob channel playlist tab. So let's do a quick recap here. Our friend finds themselves in possession of a mysterious, purportedly loaded coin. Now, observing that this coin seems quite typical and knowing nothing else about it, we fashion a statistical test. We use the normal approximation, a standard normal or Gaussian distribution to approximate the sampling distribution of our sample statistic proportion of heads. When we set our significance level to 0.02, or simply 1 in 50, our critical region under the standard normal model of our null sampling distribution is any value of our test stat that's less than or equal to -2.3 or greater than or equal to +2.3. Now, in our little made-up experiment, we flipped this coin 50 times and got 30 heads. Our observed sample proportion is therefore 3/5. We plug our result along with our hypothetical value for the true population proportion of heads, along with our sample size, and we end up with a calculated observed test statistic of about 1.41. Since this test stat, this particular value we obtained, does not fall in the critical region, we do not reject the null hypothesis, or we fail to reject the null. In our little make-believe experiment with this coin, our 50 flips or trials, we did not encounter sufficient statistical evidence to overturn the assumption that the coin is fair. So let's imagine another example. Same basic setup as before with our coin. We assume that the coin is fair, and we are interested in whether or not it is, in fact, loaded. Again, we set our significance level to 1 in 50. We still use, of course, the normal approximation, so our critical region is the same. However, let's say that in our experiment, we flipped it not 50 times, but rather 200 times, and these flips produced 120 heads. Now, the first thing to point out here is that our proportion of heads is the same as before, as with our original example, 3/5. This means that in calculating our test statistic, the difference between our observation and our hypothetical parameter value is the same as before, 1/10. What has changed, however, is our sample size, the number of trials. This directly affects our standard error. Increasing the sample size shrinks the standard error. And so here, in this example, our test statistic does in fact land in the critical region, and we hence reject the null hypothesis. That is, we conclude that the coin is loaded. In our little make-believe experiment this time with our coin, our 200 flips or trials, we did in fact encounter sufficient statistical evidence to overturn the assumption that the coin is fair. Just so we can say we did it, our test stat is about 2.83 here. Our p-value is the area of our normal PDF that corresponds to the combined regions here in the two thin gold regions here in the tails. This is a rather small number, about 1 in 215, something like that. So while we're at it, let's run through another very different looking example. So for this example, we're going to bring back an old Quantslob friend, our beloved bolt making machine here, a machine which makes bolts. So isn't that nice? We got our bolt making machine. Remember that, harkening back to our foundational series? Okay, so let's say we have a batch run of 200,000 bolts. And so this is going to be our population of interest. To each bolt, of course, we have numerous attributes. But for the sake of this example, let's say we're interested in the two-level categorical attribute has high ultimate tensile strength. Basically, does the bolt possess especially high strength? Now, if you're a big fan of fasteners, and I mean, after all, who isn't, you'll know UTS can also stand for Unified Thread Standard, so we could also QC test our bolts based on the standard tolerance. It doesn't really matter. This is just an example. Okay, so anyway, if our bolt making machine is working correctly, 4/5 of the bolts it produces will have high UTS. This is our default value, and so we hypothesize that this is the proportion in our run of 200,000 bolts. We cannot test all 200,000 bolts in our population. In fact, some fastener QC tests actually destroy the component, so it's completely impractical. What we can do, however, is select through a mechanism of random selection a subset or a sample of 200 and test them. Now, in our coin flipping experiment, we wanted to detect a loadedness of the coin, and that could mean that either heads or tails were favored. With a QC test, we are usually more focused on a particular region in our parameter space. In particular, our concern is that our beloved bolt making machine may not be performing as it should. Or if you prefer from a business perspective, that this batch run of 200,000 bolts may not be up to the standard of excellence of which our customers have come to expect. This is reflected in our alternative hypothesis. Here, our research inquiry is concerned with the prospect that the true population proportion of high UTS bolts is less than 4/5. If so, we may have to downgrade the specification and reduce the price of this batch run, and maybe even have our bolt making machine inspected and serviced. So for this test, let's set our significance level to something a little bit more traditional. Let's say 1 in 20. Remember the basic logic of our critical region here. A space that contains values that are improbable given that our null hypothesis is true, and also potentially highly probable if the alternative is true. Our critical region is hence concentrated here on the left tail out here of our normal model. So let's say, for the sake of example, after we randomly select our 200 bolts and perform our quality test, that 165 have high UTS. So now we plug our hypothetical parameter value 4/5, our sample size 200, and our sample statistic 33/40 into our trusty equation and get something about, 0.8839. Here, our test statistic does not land in the critical region, and we hence fail to reject the null hypothesis. That is, we do not conclude our bolt making machine is underperforming, or if you like, we do not conclude that our batch run is substandard. Our p-value here is the area under our normal PDF that corresponds to the region less than or equal to about 0.8839. Be reminded that we know this is our p-value region because it contains values that are rare if the null hypothesis is true, and also contains values that may be very likely if the alternative is true, and must also include our actual observation. Whatever you do, do not miss our action-packed mini-series grand finale, and That's it. That's going to do it this time around. Thank you very much for tuning in. I really do appreciate it. Don't forget to stay tuned for more Quantslob. Greetings and welcome to another installment of Quantslob. This is 26 in our basic application series. This time around, we're going to close out our practical series on hypothesis testing of a single proportion. If you want to enjoy the blow-by-blow action, and who would not, I suggest you watch this mini-series playlist in full. You can find it under the Quantslob channel playlist tab. For this installment, we're going to work through one more example, then offer some concluding diagnostics. So, for example, suppose we have a soon upcoming election between two and only two candidates, candidate A and candidate B. Now, we can imagine a population of registered voters who self-report that they are very likely to vote in this upcoming election. So let's say this population is very large, say a few tens of thousands of people. So we're going to obtain survey responses from a sample of 250 individuals from within our population concerning whom they support. Now, there's actually a few ways to apply a statistical test to this scenario, but for the sake of simplicity, let's ask the research question: does a preponderance of individuals from within our population support candidate B? Well, what's a preponderance? It's any proportion greater than 1/2. So quite directly, here is our hypothesis pair. And so let's set our significance level to 1 in 20. Remember that our critical region is a space of values that contains test stat values that are unlikely if the null hypothesis is true, but may be very likely if our alternative hypothesis is true, and that defines an area under our test stat sampling distribution equal to our significance level. By the way, throughout, we're using the standard normal distribution, same distribution every time, and after you've done enough of these, you start to memorize these critical regions. Any statistician can tell you in their sleep that our critical region here is any value greater than or equal to about 1.645. And if you don't have this stuff memorized, it's not a problem. You can use a table or software or web widget to obtain the critical region here. So let's say, for example, that in our sample of 250, 133 say they support candidate B. We plug our values into our trusty function that converts our observed sample proportion into our standard normal test stat approximation and obtain a value of about 1. The value 1 is not in our critical region, and so as a consequence, we fail to reject the null hypothesis. Or said another way, we have insufficient statistical evidence to conclude that a preponderance of likely voters at large support candidate B. So we've come this far. Let's bust out with the p-value. Our p-value region is, of course, one that contains values that are rare if the null is true, and values that may be common if the alternative is true, and that contains our observed test stat. The p-value is the probability of this region, or the area of our distribution over our p-value region. By the way, another way to describe our p-value region is a region that contains values that are more likely if the alternative hypothesis is true than if the null hypothesis is true. And of course, that also contains our observed test stat. Our p-value here is about 16%. 16% is not less than or equal to 5%, our significance level, and so we fail to reject the null. We already know this. So let's do a quick diagnostic on this example here. Of course, the question we'd really like to answer is, will candidate B win the upcoming election? Applying our statistical test in the way we have been would require access to the population of all people who actually voted. This population is not only imaginary, but completely inaccessible, not until the actual election takes place. Of course, still, limiting our research question to simply whether candidate B is favored among likely voters does possess value in and of itself. This is a theme for future Quantslob videos, but without intimately knowing the details, I think it would be intuitive for most to understand that nonetheless, it would be tricky to get a sample of people that represented the target population. In other words, it would be difficult to obtain a representative sample. People who would participate in our survey would likely be outspoken, and those with sufficient free time to complete our survey. This problem is called survey bias, or more broadly, sampling bias. So, before we close out this mini-series, I want us to revisit our original coin flip experiment. And here we find a much more subtle and insidious factor at play. we never described how exactly we were executing our coin flips. Consider that an illusionist loaded coin here is one that appears typical but is physically altered internally so that one side is heavier than the other. This can be achieved, for example, by laminating a thin disc of lead with a thin disc of aluminum. This alters the coin center of gravity when it's stood on edge. This physical alteration has essentially no effect on the outcome of a flip if, for example, the coin is caught out of mid-air, which may be why this practice is so common. Well, that and the prospect of not wanting to have to search for it if it rolls under a couch or something. In fact, this sort of alteration has only really a negligible effect on the outcome of a flip, even if the coin is allowed to freely land on a surface, provided that the surface is giving or yielding, like a shag carpet or something. This alteration does affect the outcome, albeit slightly, if the coin is allowed to freely land and bounce around on a hard surface, and a little bit more so if the coin is spun on edge. Now, in our earlier video titled simply The Sample, this was perhaps to the surprise of some viewers, really not about samples or data sets at all, but really about extolling the critical importance of how a sample is realized. The revelatory process, we called it, the mechanism. Last piece of business here. In this mini-series, we relied on the standard normal or Gaussian distribution to model our sampling distribution. There's a very long tradition in this approach. One nice thing is that creating our critical region and calculating our p-values is very direct. We use the same distribution every time, a standard normal or Gaussian distribution. We can, in fact, perform our single proportion hypothesis test using an exact test, which makes use of the binomial distribution. And that's it. That's going to do it this time around. That closes out our mini-series. Thank you very much for tuning in. Don't forget to stay tuned for more Quantslob. Greetings and welcome to another installment of Quantslob. This is 27 in our basic application series. This time around, we're going to pick up our ongoing series, The Basics Accounting, with part 3. Combinations are all about selecting unique items or values from within a collection. Now with pizzas, to resume our previous example, we are not typically concerned with the order of the toppings. In other words, if we order, say, a mushroom and salami pizza, the order in which the chef places these two toppings atop the pizza does not change the fact that it's a mushroom and salami pizza. Toppings on a pizza in this way can be considered an example of a combination. The real world certainly offers many other fairly routine examples of combinations. Poker hand in a game of 5-card stud is another example. As far as the rules of the game goes, how we arrange our 5 cards does not change the value of our hand. However, we may encounter a situation where the selection of items or values from our collection occur in a certain order or fall into a specific arrangement. Such a situation is called a permutation. And of course, permutation is named after, you guessed it, the great frame welder and mathematician Cooter permutation. And if you've seen the previous 2 installments in this series, the answer is yes. Yes, we're going to go ahead and beat this shtick right into the ground, evidently. The permutation is not named after Cooter here, nor is it named after anyone. But the good news here is that if you've ever wondered what sort of comedy writers you can hire for $10 and a Batman Pez dispenser, there you go. Wonder no more. Keep this thing moving forward here. So let's consider an example of a permutation. Suppose we have 7 track finalists that are going to compete. And in the usual spirit of such competitions, first place will be awarded the gold medal, second the silver, third the bronze. The question here is how many different ways can these 7 competitors medal? This should feel similar to a combination, except here the arrangement of the 3 winners matters. Now, if we are indifferent to how our 3 winners medal, then this is simply a 7 choose 3 problem. However, in this example, the chosen 3 can medal in a number of different ways. And well, it turns out that if we have k unique objects, they can be arranged in k factorial ways. So in this example, 3 factorial equals 6. The consequence is actually fairly simple. A permutation increases the number of possibilities over a combination by a factor of k factorial. So Common notation representing our permutation is quite similar to that of a combination, except we replace the capital C for combination with a capital P for permutation. For our actual function, we simply multiply our combination function by k factorial. And this actually simplifies the mathematical representation here. 7 permute 3 is 7 factorial divided by the factorial of the quantity 7 minus 3, 210. There are 210 ways in which 7 finalists can meddle. Now, up to this point, even if you're new to counting combinations and permutations, I'm hoping that what we've looked at here isn't overwhelming. I mean, after all, pizza toppings, medals at a competition, we can deal with that, and the math isn't too crazy. It's pretty manageable. But I'll tell you that, maybe somewhat surprisingly, counting can get extremely complicated. Some people, it seems, has maybe a slightly more natural intuition for it than others. Part of the reason involves the intuition around how scenarios can be cast as a counting problem in the first place. So I'll give you an example. Consider the question of how many different ways 3 of 6 chairs can be occupied without concern to the identity of the 3 occupants. Now, on its face, this scenario seems quite different than the pizza topping scenario. After all, with the pizzas, we are taking 3 of our 6 available toppings and placing them onto the pizza, whereas with seating, we're sort of doing the opposite. We are imagining how we can place 3 occupants or people onto the seats. However, it turns out that from a mathematical standpoint, they are really the same problem. In both, we can think of it this way. We have 6 slots and 3 objects. With the pizzas, the 6 available toppings are the slots. With the seats, it is the seats that are the slots. And that's it. That's going to do it this time around. As is always the case, thank you very much for tuning in. I really do appreciate it. Don't forget to stay tuned for more Quantslob. Greetings and welcome to another installment of Quantslob. This is 28 in our basic application series. This time around, we pick up our ongoing series, The Basics of Counting, with 4. It turns out that we can combine these two hopefully familiar concepts and arrive at one of the most, if not the most, important distributions in all of science, certainly among discrete distributions. But as a fair heads up, getting to our destination in this video is going to involve some mental somersaults. It's a little mind-bendy, so to say, so just hang in there. Let's return to our beloved pizzas. If we have a total of 6 available toppings, we can make a total of 64 different pizzas. And if we look at Pascal's triangle and ignore the apex, 64 is the sum of the numbers in row 6. It is also 2 raised to the power of 6. In fact, the row totals in Pascal's triangle equal 2 raised to the power of the row index. So let us imagine that someone has ordered one of each type of pizza made from our 6 available toppings. If someone were to ask what proportion of these pizzas have exactly 3 toppings, we can get to our answer directly. There are 20 pizzas with 3 toppings and a total of 64 pizzas. Therefore, our answer is 20 divided by 64, or simply 5/16. This is direct here because the 6 toppings are evenly distributed among our pizzas. After all, there is 1 of each type of pizza. Okay, so that's not going to win anyone a Nobel Prize here, but things do get more interesting. Suppose now someone were to ask what proportion of our 64 pizzas have garlic. Well, it turns out that 1/2 of our pizzas have garlic, 32 of them. And it turns out that this is true for all of our toppings. 1/2 have onion, 1/2 have salami, and so on. So is this obvious? Well, we can kind of come to understand why this works by noting that if we exclude garlic originally so that we have only 5 available toppings, there are 2 to the 5th, or 32 total pizzas we can make. And if we add another topping, garlic, for example, as we already know, there are 64 total pizzas we can make. Therefore, it is fairly reasonable to understand that 32 of these pizzas, or 1/2 of the 64, have garlic. Gets better. Suppose we set aside all the 32 pizzas with garlic and someone were to ask what proportion of these have salami. Well, it turns out the answer is the same, 1/2. That is, of our 32 pizzas with garlic, 16 also have salami. Or said another way, given that a pizza has garlic, the proportion with salami is 1/2. And if we were to set aside all the pizzas that have garlic and salami, all 16 of them, and someone were to ask what proportion of these have, say, mushroom, the answer is the same, 1/2. Just to clarify the symbology here, this statement here could be read as the proportion of objects, in our case pizzas, that have mushroom, given that they have garlic and salami, is 1/2. Another way to say this conversationally might be something like, of all the pizzas that contain garlic and salami, 1/2 also contain mushroom. Now, if we subset our pizzas based on the presence of any, none, 1, 2, 3, or 4, or 5 toppings, and ask what proportion of these contain one of the other toppings, the answer is always going to be 1/2. So, to help us get to the punchline for this video, we're going to do something that on its face may seem to really complicate things. We're going to completely reverse our approach. Instead of defining our collection of pizzas ahead of time, like one of each kind of pizza, we're going to specify the constant prevalence of each and every topping, then see what sort of collection of pizzas we end up with. So for example, we're still going to use our 6 available toppings, but suppose now that the proportion of pizzas containing any given topping is not 1/2, but rather, say for the sake of example, 2/3. 2/3. That is, if we consider only pizzas with a pre-specified subset of toppings, the proportion of those containing one of the other toppings is always going to be 2/3. Now, suppose someone were to ask what proportion of this new collection of pizzas has, for example, exactly 3 toppings. And you may think that this is just insane. I mean, no human being or even like some sort of super pizza being could ever solve a problem like this. But just when we think all is lost, well, I have to confess, we struggled coming up with the metaphor. I mean, I think that this is okay. Mr. Combination meets misproportion. They seem pretty happy here. We also considered, hey, you got some proportion in my combination. No, you got some combination in my proportion. But, who's going to get that reference? And honestly, I'm far from convinced that that is even amusing. Anyway, what do we end up with? Behold the binomial function, or the binomial distribution function. So let's break this down. Let's drill into this here. Okay, so here we input the number of pizza toppings, and we also input the total number of available toppings along with our proportion representing the constant prevalence of any one topping. And the function hands us back the proportion of pizzas within our collection with the specified number of toppings. So now let's make use of this on our original setup, where we have a collection of 1 of each kind of pizza. 6 choose 3 is 20. 2 times itself 3 times 2 times itself 3 times is 64. 20 over 64, which simplifies to 5/16. We already know that. Same answer as before. But now let's try this with our new collection of pizzas. Okay, so 6 choose 3 is still 20. Combination part stays the same. 2/3 times itself 3 times is 8 over 27. 1/3 times itself 3 times is 1 over 27. So our answer here ultimately is 160 over 729. There's no common integer factors, so this does not simplify. In decimal form, we have about 0.2195, or a smidge under 22%. So check this out now. Interesting, when the constant prevalence of each topping in our collection is 1/2, the proportion of 3 topping pizzas is greater than when the prevalence of each topping is 2/3. I mean, after all, 31% is greater than 22%. Now, we can summarize our 2 collections of pizzas using a table to show the distributions of number of toppings. So here, K is the number of toppings. The next column, the middle column, shows the proportion of pizzas for each of the possible number of toppings, where the prevalence of each and every topping is 1/2. Our original collection of 64 pizzas we've been working with originally would be an example of this. The far right column here shows the proportion of pizzas for each of the possible number of toppings, where the prevalence of each and every topping is 2/3. Most recent example. Notice that no topping pizzas, 1 topping pizzas, 2 topping pizzas, and 3 topping pizzas are more popular within our first collection compared with our second collection. And the opposite is true for 4, 5, and 6 topping pizzas. By popular, we can also call the numbers here in the middle and right column relative frequency. Now, before we close out this installment, and we're also closing out season 3 of Quantslob, an exciting new feature here, our Quantslob challenge. Okay, ready? Suppose the prevalence of each and every of our 6 toppings is not 1/2, nor 2/3, but rather 1. What sort of collection of pizzas might we have, and what might the distribution of number of toppings of such a collection look like? We're going to pick this up with our soon upcoming season 4 kicker, part 1 of summarizing data, and that's it. That's going to do it this time around. It was a really fun first 3 seasons of Quantslob. Thank you very much for being a part of it. Whatever you do, don't forget to stay tuned for more Quantslob.